Hi, Year 12. This is just a review of the 2022 Independent Trial. And before I start, as you can see here, I've referenced each of these answers in the books that you have. And these are the books that I'll be referring to. You've got all of these, and this is the modules book, as you can see, communication, and make sure that you've done all of the questions in this book. This book is particularly handy because it's got all of the questions that relate to the 10 units in this book here, and also it's got solutions, and that's a really good way of learning how to do particularly the mechanics questions. Let's start with the multiple choice. Question one, which best describes the use of concrete in bridge building? Now, you know, concrete has got a high compressive strength, and it hasn't got a high tensile strength. It's when it's not a low cost, so B is the correct solution there. Correct response. And you can see this on these pages in the red book. When I haven't referenced either book here, it's the red book. Question two, which material is best suited for the use as a pedal crank arm on a lightweight, low-cost bicycle? Now, a lightweight, low cost, they're the two criteria that you're looking for. Grey cast iron's too brittle, drop forged medium carbon steel is too heavy when it says lightweight. Titanium alloy is too expensive. And so the answer here is D, aluminium alloy, and you'll be able to see that on page 52 of the red book. Mechanical lifting devices have generally replaced manual lifting in today's society. What's the main reason for this? Correct response is D, the development of hydraulics and materials technology. And each of these will be incorrect. Some of them are correct, but this is more correct with some of these responses that you see with the multiple choice. So make sure that you read all of the responses here before you select the correct one. And you see this on page 71 to 73. What manufacturing processes produces grain flow in metals? Just have a look at page 57 to 58, and that'll explain what grain flow is. Shell molding doesn't produce grain flow. Investment casting doesn't produce grain flow, and full mold doesn't. So rolling, forging, and hammering produces grain flow in the metal, and it gives it directional strength when you have a grain flow in the metal caused by rolling, forging, or hammering. Well, the main advantage of using CAD, you can see this on page 17 of the communications workbook. These other responses other than C are not correct. Accurate drawings that are easily stored. You can just store them as digital files, whereas the other method of drawing on paper, you've got to have a lot of storage space. It's easily edited and it's easily communicated, and that's really important because of the collaboration that's required with engineering nowadays, international collaboration. So question 6, a 10-kilogram block sits on a ramp inclined at 20 degrees. If the coefficient of friction between the block and the ramp, mu, is 0.25, which statement is correct? The way that you do this is that you've got your block on the ramp, and the weight force down is mg sine theta. That's dragging the block down or tending to get the block moving down the plane. And the friction force of friction is acting upwards because the tendency for motion is down the plane, and that equals mu n. And n is the normal to the plane. The force down the plane is mg sine theta. The normal is always mg cos theta. So if mg sine theta is greater than the force of friction, then A is correct. Now, it will accelerate down the ramp. Now, if mg sine theta is greater than the force of friction, it won't remain stationary. The block will move down the ramp at a slowing rate, and that's incorrect, because if you hold an object above the Earth, it will accelerate at 10 meters per second. And this is exactly the same situation with this block. It will accelerate down the ramp, just like dropping an object. So the block will move down the ramp at constant rate, which it won't. So A is correct if mg sine theta is greater than the force of friction, worked out here. So mg sine theta is 34.2 newtons, force of friction is 23.5, therefore A is correct. Question 7, a copper water pipe and copper saddle shown. Now, so there's the water pipe, and that's a saddle. You didn't have to know what a saddle is, but everyone knows what a pipe is. Assuming the saddle is made from mild steel, so this saddle is made from mild steel, and both are in a moist environment, what's the expected outcome? Now, when you've got two dissimilar metals in contact in a moist environment, the metal that's higher on the electrochemical series will form the anode, and therefore it will corrode. And when you've got two metals in contact, it's called a galvanic cell. And so the metal higher on the electrochemical series will give up electrons to the cathode, and this will become the cathode because copper is lower than steel on the electrochemical series, or iron. And so this will be the anode, and that will be the cathode. And the cathode will consume the electrons coming from the saddle. So a galvanic cell will form, and the saddle will become anodic and corrode. And you can see that on page 81 in the red book. Pure clay is rarely used to make ceramics. What are the main reasons why non-clay materials, and these are called non-plastics, are added to ceramics? They're added due to the effect of them in reducing shrinkage. You really don't want a lot of shrinkage when they're in the kiln. Also, they act as a flux, which allows the particles to bond together during firing, and it makes it easier to shape. These non-plastics make them easier to shape. That's on page 149. Number 9, a gear train consisting of 3 gears having an efficiency of 80% is shown. What is the mechanical advantage of the gear train? If you go to page 69, you'll see that when you've got a gear train or you've got pulleys, the velocity ratio is the diameter of the driven over the diameter of the driver. And you can see with this setup here, you've got an idler gear here, and all the idler gear does is changes the direction of the driven gear. So if you've got a big driver and a small driven, the small driven will go faster than the driver, and the velocity ratio is the distance the effort moves over the distance the load moves, or the velocity of the effort over the velocity of the load. So the idea is you use the reciprocal, and you'll be able to see that on page 69. And so velocity ratio is the diameter of the driven over the diameter of the driver. So it's 18 over 22, or 9 over 11. And that will give you the velocity ratio. And you can see that it's less than 1. And that's because this is going slower than that. Then the mechanical advantage is the efficiency multiplied by the velocity ratio, which is 0.66. And so that's the answer is response C. With reference to glasses, which statement is true? This is the correct statement. Glasses can have an amorphous structure or a stronger crystalline structure. When glasses are crystalline, they're much stronger than the normal soda lime glass that is made for windows and everything. Glass hasn't got a high tensile strength. Glasses are stronger and have higher optical clarity if the structure is crystalline, and that's incorrect. If a glass structure is crystalline, it has a lower optical clarity than a normal window glass. Question 11, in a tensile test, which of the following represents the engineering strain? Engineering strain is the change in length over the original gauge length. Remember, engineering is the original gauge length, and engineering stress is the load over the original cross-sectional area. So response A is correct, and that's on page 33. Question 12, which best describes a geotextile? A geotextile is a polymer that's used to separate, filter, drain, protect, and reinforce soil. So D is correct here, and that's on page 136. Here you have a simple electrical circuit with 4 resistors loaded with a 12-volt, 60 amp hour battery. You've got how long will the current flow in the circuit with that 60 amp hour battery. So the way you do this is you've got this circuit here is 2 resistors in parallel. So you work out what the total resistance is there. So total resistance is the resistance in parallel plus the resistance in series. Resistance in parallel is 1/R, which gives you 2/5. So therefore the parallel resistance is 2.5 because you've got the reciprocal there. And then the resistance in series is just the addition of all the resistors, 3 plus 3 plus 2.5 from that there. So that gives you 8.5. Total amps is potential difference over resistance. So you've got 12 over 8.5. So you've got 1.41 amps flowing in the circuit. And all you've got a 60 amp hour battery. And so you divide it by 1.41, and this isn't a bad way of doing it. Make sure you put your units in there, and they will cancel just like numerical values, and that will leave you with hours. And so the answer there is 43 hours, which is response A. Question 14, which metal best exhibits passivation? That was spelled incorrectly, and we didn't pick that up. Passivation is the resistance to oxidation as a result of a natural oxide that forms on the surface of metals, and stainless steel, aluminium, titanium are passive metals. They exhibit passivation. And stainless steel is the only one here. Low carbon steel doesn't. Tempered high carbon steel doesn't. Hardened tempered copper alloy doesn't. So you can see that on page 85. So stainless steel there is the only metal that exhibits passivity. A tensile test, question 15, a tensile test fails at a load of 33 kilonewtons. If the original diameter was phi 10, which is 10 millimeters diameter, and necking reduced the diameter at fracture to phi 6, what's the true stress? If you go to page 39, you'll see that true stress is the load divided by the diameter at fracture. And this is how I want you to set out your solutions to get marks. If you get or not in multiple choice, you won't, the examiner won't see your solutions. But in extended response questions, you should set it out like this. So you put down your formula, which is given to you on a formula sheet. I like to put true and area at fracture there. And and you put all your data here. Make sure you put your units there, so you're showing the examiner that you know what units you're going to use. Make sure you don't put kilonewtons in. You've got to put it out to its total numerical value. And the area, I've got area at N, which is necking. Show that you know the area, pi r squared. Put all your numerical values in, multiply it by 10 to the minus 6 because you've used millimeters there to bring it to meters squared. And I always like to work out the numerical value here so that you only have to put that under here. You don't have to write all this out. And I haven't put 10 to the minus 6 there because my answer I want in megapascals, and 10 to the minus 6 comes up to be 10 to the plus 6, which is mega. And so you've got the true stress at 1167.1 megapascals, which is response D. Next question, question 16 on page 6. The drawing below shows a nut and washer suitable for an M12 by 1.5 bolt. Now, make sure you know what this means. M is the metric profile of the thread, 12 is the diameter in millimeters, and 1.5 is the pitch. And the pitch is the distance between one peak of the thread to the adjacent peak of the thread. Now, you've got to learn all of this on page 16 of the communications workbook, the yellow book. There's no substitute for not learning it. So you know that across flats here is 1.6D, so it's 1.6 times 12. The width of a nut is 0.8D. The across corners of a hexagon is 1.8D. The diameter of a washer is 2D, and the thickness of a washer is D on 4. And so when you work all this out, you'll see that C is the correct response. Question 17, which statement best describes the process of doping semiconductor materials? Now, as you know, doping increases the conductivity of a metal, of a semiconductor. And it's really important to learn about this on page 155. And so C is the correct answer there. It increases the conductivity by increasing the number of electrons and positive areas in the semiconductor. An aircraft pitot tube is shown below. And this is explained well in the red book on page 75. And a pitot tube measures the airspeed of aircraft. It also measures the airspeed of liquid and gas velocity in industry. In fact, when I was training, I had to use one of these to find the velocity that this fan was pushing out in the heat treatment room. So that's question 18. Question 19, and the year 11 students should be able to do this now. So you've got a block of metal here. It's 20 by 8, that's 20, that's 8. And you've got a phi 8 hole drilled in there. And it's subject to a 50 kilonewton force. Now remember, 50 kilonewtons is quite significant. It's equivalent to hanging a mass of 5 tons on it. Remember, you move the decimal point 1 place to the left, and that'll tell you how many tons it is. So what's the maximum stress in the metal plate when it's subject to the 50 kilonewton load as shown? Now, obviously, it's going to fail where there's least material, and it's going to fail across there. So you've got to work out the cross-sectional area of this section here where the hole is. And so this is the hole here. It's 20 by 8 deep. So the metal that is left there is 20. Take 8 away from 20, so it's 12 by 8. That's the area of tensile stress. So same routine, set it out like this. Tensile stress is equal to load over cross-sectional area, where the load is 5 times 10 cube newtons. The cross-sectional area is 12 by 8, which I worked out there, multiply by 10 to the minus 6, and you get 520.8 megapascals, and that's response B. The other thing you've got to work out with these is the force required to punch the hole, because if you have a compressive stress in the punch greater than the strength of the metal, it's going to disintegrate. And I've seen that happen many times. This is a different formula here for the area. That's the first thing that we look for, that the area is different. And so shear stress is equal to load over area of shear, where the shear stress is 20 times 10 to the 6 pascals. Don't put mega in. The area of shear is going to, the punch is going to shear around the outside and then cut its way all the way through. So it's the perimeter times the thickness, and it's pi d times thickness, and you've worked out a numerical value here. And you transpose the equation, so make P the subject. So you've got area of shear there, multiplied by the shear stress, and the 10 to the 6, 10 to the minus 6 cancel, and so you got 50.3, and so D is the correct response there. Okay, section 2. Modern turbine blades are cast as a single grain. They've been cast as a single grain since the early 70s, which eliminates grain boundaries from the blade. And you can look this up on YouTube. It's a really fascinating method that they use. They call it a pigtail that they force the metal through. And the turbine blade just grows as a single grain, so you haven't got any grain boundaries in it. Explain how the surface properties of the blade are enhanced by the elimination of grain boundaries. Now, you've got to explain it. If you just state it, say, and you don't say because or explain your statement here, you won't get full marks. And so the without grain boundaries, you've got greater resistance to thermal fatigue. It's more corrosion resistant. Failure can occur along grain boundaries, so it's it will have higher strength, higher melting point, and it also, because you've only got you haven't got any grain boundaries in it, it will contribute to greater thermal efficiencies. And this is on page 13. You'll see the effect of grain boundaries. Not on turbine blades, but you'll see the results of having grain boundaries. Turbine blades are generally manufactured from nickel-based superalloys to resist the high operating temperature in a gas turbine engine. Explain how alloying strengthens a metal when compared to the pure metal. And just this is well explained in the Red Book, page 54. And simply, you've got a disparity. Now, here's an explanation here. So one statement won't do. And the response is 3 here. And see these marking guidelines down here. And you'll always see one correct response will get 1 mark. And so I'll let you read that, but very briefly, if you've got a disparity of grain sizes, that when you apply a plastic deforming force to it, it will reduce the number of slip planes, having those stranger atoms, and it will tangle the dislocations and just basically result in the material becoming stronger than the pure metal that it was made from. Next question. Most turbine blades in gas turbine engines are made by investment casting or the lost wax casting. And this is explained on page 56 in the red book. Using the diagram to assist your answer, describe the process. Now, there's 3 marks here, so we would expect to see 3 definite responses. We'd want to see the first response is a accurate metal mold is made and wax is poured into that, and you've got a wax replica of the turbine blade. And then the next response would be that the turbine blades are put onto a tree of wax and then covered in a refractory liquid, then powder, liquid, then powder to build up the mold. And then the third response would be the tree with all the refractory would be put in upside down in a furnace, slowly heated, and it would melt the wax would pour out, and slowly heating it would fuse the refractory around the outside, so you've got a perfect mold on the inside. And then the liquid metal of the turbine blade would be poured in and then allowed to cool, and the mold is broken up, and then the turbine blades or the material or the part would then be exposed and then machined if necessary. Generally, they don't need a great deal of machining. CMC turbine blades, ceramic matrix composite turbine blades, are being trialled for future use in gas turbines. So, you know, ceramic resists heat, it doesn't corrode, it is got a high compressive strength, it doesn't creep under constant force. So they're the sorts of things that you have to be aware of. Now, the question says, describe 4 possible benefits to society gained from the use of ceramic turbine blades in aircraft fan jet engines. So if you just say ceramic blades can resist higher temperatures, that's a statement, it's not a description. You've got to add the characteristics and features of this property here. And it will produce a more efficient engine, resulting in less cost and freight. So you're actually answering what they're asking. Okay, they're lighter and resist cyclic loads such as creep, which produces a safer engine, right? You've got to make sure that you put that there because that's a description. And ceramic blades have greater durability, therefore reducing maintenance. And here's the important part of it. To answer this question, benefits to society, providing less cost for operators. And they have much greater resistance to the intense corrosive atmosphere. And here is the justification, thus enhancing the cost and safety benefits for society. Now, this was poorly answered, and when I visit you in the next couple of weeks, I'll be going through this particular question. I'll be doing it for you again, but I'll just quickly go over it now. So you've got an orthogonal drawing here. You've got the right side view, front view, and top view, and I think I gave you a 3D drawing of it up here. And here, this is the answer. This is the development of A, B, C, D, right? So you've got to develop that, A, B, C, D, and C, E, F, D, those 2 sides. Now, in the HSC, I'm sure you won't be asked to develop more than 2 sides. If you were asked that be unreasonable because it's repetitive and it takes a lot of time. Even though this question's worth 6 marks, you really don't want you to have to be doing repetitive actions during an exam. Now, this is explained in pages 29 and 30 in the communications workbook, but I'll just explain it fairly quickly now. Every line on this development has to be a true length, and the only time you see a true length in an orthogonal view is if the projection of the line in the other view is either a point or it's horizontal. So let's have a look at this. We're going to ask ourselves, is BC a true length? You look in the other view, you see it's a point, so therefore that's a true length. We're going to say, we're going to ask ourselves, is DF a true length? You look in the other view, you see DF is horizontal, so therefore that's a true length. And in fact, the projection of that up here is a true length as well. But let's have a look at CD. You ask yourself, is that a true length? You look down here, there's CD. It's not horizontal. It's not a point, so therefore that's not a true length. Now, how do you get CD as a true length down here? Well, this is how you do it. And this is the important part. If you put your compass on C and open it up to D, you're not getting the true length of CD because it's angled up. But what you're getting is the base length of the triangle. So here is CD there. So if you put your compass on that there, you're getting that base length of the triangle, the base length of the imaginary triangle, so that this line goes right down the bottom and the base length of the triangle goes there. So that if you know the height of C above the base as a true length, and you've got the true length of the base, you've got a triangle with 2 true lengths, and so the hypotenuse of that triangle has got to be a true length. So to get the true length of CD, put your compass on here, you come down here, see that line? That's a vertical line there. So that's the true length of C above the base. And you use this length here to go out here somewhere. Let's say it's out here, there. I didn't mark these because you don't have to. And then, so that's a true length of the base. That's a true length of the height. And so that's got to be a true length of CD. So I'll just show you how you get that point there, right? So you go out to AD. Is AD a true length? There's AD there in the top view. You look here, it's a point, so therefore that's a true length. So you put your compass point on A, and then you scribe an arc out there. So D lies somewhere along that arc. So I'm going to go from B, get the true length of B to D. So here's, put my compass on there, go out to D. I'm getting the base length of that imaginary triangle. I know how high B is above the base. That's how high B is above the base. And I'm just going to use that distance, mark it down here. Let's just say it's that. And so that's the true length of the base of the triangle. That's a true length of the height of B above the base. And then set my compass up on that. And then put my compass on B and open it out to that distance there. And then you put your arc there, and so you've located D. And that's how you do triangulation. And it requires practice. And the best way to do this is to do a development. And there's plenty of examples in the yellow book. Cut the development out and put it over the answers in the back of the book for that particular question and see how accurate you are. When we mark these, we put a mask over it, and if you're more than 1 millimeter out, you could lose marks. Next question. This is an orthogonal exploded, it's an exploded isometric drawing, and you're asked to do a section, front view, looking in the direction of the arrow there. Now, a couple of things about this exploded isometric drawing. You've got a pitch circle diameter. Now, pitch circle diameter is the diameter of the center line of the circle that goes through the center of equally spaced holes, like the wheel nuts on your car. They're all on a pitch circle diameter. If you went to buy new wheels for your car, you've got to know what the pitch circle diameter is and the offset of the wheel. Now, so this is 4 phi-10 holes on 42 PCD. So the diameter of that circle there is 42 millimeters. Now, the thing that you've got to know about this is if you do a section through the center here, which you're asked to do, you're not going to see any of those holes because you don't put hidden detail in a section. So the rule is that you've got to rotate that hole so it comes up the top, and so that you'll see that hole in section. So this is what I've done here. I've rotated that hole up to the top, and so the distance between the center line of the object and the center line of the hole will be 42 divided by 2, which will be 21 millimeters. So that distance there will be 21 millimeters. So you've rotated that hole so that you can actually see it. Now, the other thing that you've got to know is you don't section the whole lot if the whole object is symmetrical. Now, if you do section the whole lot, you'll still get 4 marks for it if you do it correctly, but it's a waste of time. In drawing offices, you don't section symmetrical objects fully. You just do half section. So you've got this steel bush here that is, you can see that it's phi-18 and the hole is phi-18. And so that's a force fit. It's called a force fit. You press that in to the boss there. And so that's a different material to that. And so you have to hatch it differently. So this is one material here, and that's another material there. Make sure you know, look, there's no dimensions on this, so make sure you know the proportions, except the proportions of nuts and bolts and washers and threads. And if you're only showing one view of this bolt, look, see how this is shown here. If you're looking there, you'll only see 2 faces, and that's not on. You're not allowed to do that if you're only showing one view, because it could be a square. And so you've got to show 3 faces here. And the diameter of a washer is 2D, and the cross corners of a hexagonal nut is 1.8D. So the first thing that we look for when we're marking it is that there's a difference between that height and that height there. Make sure you know how to show a thread. Notice that the section lines don't go through that thread there because it's a bolt. If there's no bolt there and you just saw a thread in there, the section lines would go through that pitch or the depth of the thread. This is how it's marked. See, down here provides one correct response. So those people who left many questions blank, you're missing out on this. Most people can get 1 mark from a response. So check out 7 to 16 in the communications workbook. Question 23, a hydraulic system is used to raise and lower the front of buses for better passenger access. You've seen that. If the front of the bus is a mass of 4 tons and moves a vertical distance of 200 millimeters in 5 seconds, so as soon as you see that you've got a time here, you're almost certain to have to work out power. Calculate the power required for the upward movement if the efficiency of the hydraulic system is 80%. So power is work on time, and it is force times distance on time, or it's force times velocity. And so the output power is 1600 watts. Now, efficiency equals output over input. Now, I don't think that's in your formula sheet, but it may be. You can have a look later. The way to remember this is output has got a big O at the front, and the O is a bubble and it floats on top, right? So efficiency equals output over input. Like the efficiency of this is 80%, which is 8 on 10. So the output has got to be less than the input because it's less than 100%. And so we want to find the input. So input is equal to 1600 over 0.8. So you've got 2 kilowatts to raise that bus. And that's on page 65 and 66 of the Red Book. The bus raising hydraulic system has an input piston diameter of 15 millimeters and output piston diameter of 42 millimeters. Now, this was a gift, this question, and a lot of you still didn't do it. You've got to remember this formula because it's a derived formula. And the velocity ratio of a hydraulic system is the output cylinder diameter squared over the input diameter squared. A few of you used it, but you failed to square it. So that's the velocity ratio, and you've just got to remember it. Remember again that the big bubble floats on top. And so that's 7.84. Velocity ratio, remember, doesn't vary with efficiency because it's a velocity, or it's a distance if you take time as the same. And mechanical advantage equals efficiency times velocity ratio. And so the mechanical advantage of this system is, this hydraulic system is 6.27. A car of mass 1.5 tons traveling 60 kilometers an hour approaches a 30-degree incline. Neglecting friction, how far does the car travel up the incline if the motor is turned off at the bottom of the incline? Well, the kinetic energy at the bottom has to equal the potential energy at the top. So half mv squared equals mgh, and you get a vertical height of 13.9. Now the question says, how far does it travel up the incline? And so it's just simple trig, and you can use sine, and it's 27.8 meters up the incline. Some people got 20,000 kilometers. Now, make sure that you just look at this and just be logical. You'd be thinking it's around 30 meters going up the incline. 30 degrees is fairly steep. So just look at it and make sure that you've got a logical answer. Question D. A corrosion cell reacting on a painted mild steel surface is shown below. Explain the mechanism likely causing this corrosion cell and why the paint is blistering. So what happens here is that you get a scratch in the paint and that starts to corrode because it's in a moist environment. Now, the corrosion occurs if you've got an area where there's depleted oxygen. And so, and this is called differential aeration. And so when the anode starts to be formed underneath the paint because there's minimum oxygen compared to where the scratch is, you start to get galloping corrosion here, galloping rust. And so the anode starts to keep moving away from this cathode area. And the anode is giving up the electrons where there's little oxygen. It's just like waterline corrosion, just below the waterline where there's minimum oxygen compared to above the surface. Piles, steel piles, rust just below the waterline because of the minimum oxygen there. And so the anode starts to move away from the cathode. And you know that the corrosion product, which is Fe3O4, has got more volume than the steel originally. And so that's what's blistering the paintwork. And so we'd want sort of 3 responses from that. And as you can see here, 1 correct response will get 1 mark, but not attempting the question will get you 0. Now, these test graphs here, so I'll just go to the next page. I'll just figure out what we've got to do. You've got to determine Young's modulus, then you've got to do proof stress, determine the proportional limit for material B, and which of the 3 materials is toughest, and which is medium carbon steel. So let's have a look at this. So Young's modulus. Young's modulus is the slope of the straight line section. Some of you started to use this out here. You can't go past the limit of proportionality. It's got to be the slope of the straight line section. So Young's modulus, I've just selected that point there because it's on the line. And then it goes down here, and I made this so that it hits right on 0.2. And so it was pretty easy to work out that it's 200 gigapascals if you knew this. Remember, the slope is tan. Tan is opposite over adjacent there. So it's the slope. And so it's stress over strain, which is 400. See, that's 400 times 10 to the 6 megapascals divided by 0.2%. Now you can't put 0.2% in. You've got to make it a numerical value. It can't be a percentage. 0.2% is 0.002, and so it gives you 200 gigapascals. Now, how do you find the proof stress? Now, this material has got progressive yield, so you've got to use proof stress. See this material here? It's got a definite yield point, so you don't use proof stress for that. So proof stress, you go along the strain axis, 0.2%, and that's already been put in there. And so you draw a line up here, parallel to the straight line section. Where it hits there, you'll get the proof stress. The proof stress is 650 megapascals. But what's the proportional limit of material B? The proportional limit is where the straight line ends, right? The proportional limit up here is around about 600. The proportional limit here is about 230. Which is the toughest? You're looking for the biggest area under the graph, and material B is toughest because this will be a low carbon steel, anneal, because it's got a definite yield there. Which material would be a medium carbon steel, which can be heat treated? This material can't be heat treated because it hasn't got enough carbon, and around about 0.1%. So this is the material that is medium carbon because it is stronger, it can be heat treated, and it's got a significantly more vertical straight line. Actually, this steel here would have a Young's modulus pretty close to 200, but I had to differentiate that there. Okay, this is all on pages 33, 34, and 39 of the Red Book. Next question was not very well answered. I think only 1 or 2 of you got this right. So you've got a block of mass 10 kilograms, and the incline plane is 35 degrees. You've got to determine the force to initiate movement of the block up the plane. So the block has got the tendency to go up the plane, so therefore the force of friction will go down the plane. And so you work out what the angle of friction is. I'm going to use the 3/4 rule for this. You can't do this mathematically. It's you can, but not in an exam situation. I think a couple of you tried it, but it's quite difficult. But it's really easy if you use the 3/4 rule. So let's quickly do it, because we're running out of time. The first thing you've got to do is put all the forces on the diagram. So there's your 100 Newton force going down there. There's your normal there, and I'd put a little angle there to show that it's 90 degrees. And so that'll be your point of concurrence. And you've got your force of friction going down there. But if we put the force of friction in, we'll have 1, 2, 3, 4 forces there. And we don't want 4 forces. So we're going to add the force of friction to the normal and get the resultant. So we're eliminating 1 force, so we can have 3 forces there. And so the 3 forces will all be concurrent at that point there. And you know, the angle between the resultant of the force of friction and the normal is the angle of friction, and tan phi s, which is the angle of friction, equals mu, which is 0.2. So therefore the angle between the resultant and the normal will be 11.3 degrees. So you're using their diagram, and then you put that force in there, 11.3 degrees going up there. You move that force down here, so that it's still parallel with that, but it joins at the point of concurrence. And then you're ready to do the 3/4 rule. Now, I use Bose notation, so I've got A going around the resultant, B going between the resultant and this force, and C going around, back around there. So you put a scale in, which I haven't. Make sure you show a scale. So I've drawn that to scale, so that is CA, CA. Then the next force you've got to read clockwise is the resultant. So you draw the resultant through up there. We don't know how far it goes. Then the next force, and the resultant is AB. It's got to go through A, and so that's B up there somewhere. And then BC has got to go through C, parallel with that force. And so that's how you read off the force required to just move that, or get that block on the movement up the plane. And that's on page 77. It explains how to do that. You've got a orthogonal drawing here. What I was looking for here, it didn't matter if this went over your writing, don't worry about that. I was looking for it viewed in that direction. I was looking for the correct circles in it, and it wasn't too badly done, this question. And it's, you see pages 5 to 16 of the communications workbook. This is another question that you could do using the 3/4 rule. You had to find the reactions. And so you've only got 1 force there, you've got 1 force there, you've got 1 force there. And so you produce, and make sure that you put, when you've got a roller, you put a reaction at 90 degrees and show the examiner that you know that, because provides 1 correct response will get you that mark there. Produce that force up, and where it hits this force, this 20 kilonewton force there, that's the point of concurrence. And so the third force will go from that point down there. Then use Bose notation. I've used X, Y, and Z here. So X goes through all the way around here. That's X. And this is Y, and that's Z there. You start with the known force. Put your scale in. There's your known force. And so you draw that to scale. And that force is ZX, ZX. There's the Z, there's the X. The next force going clockwise is this force here, which is XY. It's got to go through X. So that goes up. We don't know how far it goes up. And then this last force is this force here, which is YZ. It's got to go through Z. So you just transfer that angle up there and you'll find Y. And so straight away, you've got your right reaction and you've got your left reaction there. And then you just put your protractor on there and see what angle it is, and you've got the correct reactions there. And this is the analytical way of doing it if you want to do it analytically, and you can see how accurate the graphical method is. Next question is you've got to find the force in AB here. And you can do it by method of joints, but when you're at a reaction and you've only got 3 forces acting at that reaction, you can just use the method of joints. So you know what that force is. Put your scale here. I've used Bose notation again, X, Y, Z. So this force going up is X, Y. That force going clockwise there is AB, so that's YZ. We don't know where that goes. But this next force is ZX. It's got to go through X. And so there's your force diagram, and you just scale off that distance using that scale, and you can easily find what the force is and see the sense it's pulling away from this joint here. So therefore it's in tension. The other way you can do it is you can do a section. You can remember you can section 1, 2, or 3 members, but no more than 3. So I'll put a section in here, and finding that distance there is quite involved. Using trig, you got to find this angle and that angle, and then use you got to find that length, which is quite involved. But look, this is a good way of doing it. I've put my rule on that, and I found that distance on the exam paper to be 14.4 millimeters. So I've got 1440 millimeters equals 14.4. So I've got a ratio of 1 millimeter equals 100 millimeters. And so I've just put my set square on there. I've worked out what that distance is there. It's 17.9. And so you multiply that by 100. So in using these values, that distance there works out to be 1790 millimeters. Now, if I take moments about this point here, I've eliminated the force in there, and I can find the force there. So I say sum of the moments about P with clockwise positive, P clockwise positive, and I'm taking the right-hand section. And so I've got AB times 1.79. So I've got AB times 1.79, which is 1790. I'm not using millimeters, minus 6.1 times 144. So we've worked out 6.1 from the previous question. And so the perpendicular distance there is 1440, and it equals 0, so AB equals 4.9 tension. Okay, next question is the Plee formula, and this is on page 34 of the book. Calculate the change in length of AB when loaded with the 20 kilonewton force. So we're saying that AB here is with another loading situation is subject to a 20 kilonewton force and is 4 meters long and 100 by 75 in section. So the Young's modulus for the timber member is 10 gigapascals, and you've got to find the calculating the change in length of AB. So delta L equals PL over EA. Make sure your units are all correct, and so it will change. And if it's a it will change in, it just doesn't say whether it's a tensile or compressive force, but the change delta L is 1.1 millimeters. Describe 2 advantages and 1 disadvantages of bridges to society. We 3 marks for 2 and 1, and you've got to describe. If you just say that bridges make travel easy, that's a statement, it's not a description. You say because it can eliminate many miles, which will blah, blah, blah. Okay, so make sure you describe, you don't state. And this is on page 45 in the modules book, the Rainbow book. This is a logic gate question. You had to fill in these here. This is an AND gate, right? Sorry, this is an OR gate. That's an OR gate. And this is a NAND gate. When you see it like this, it's normally an AND, but when you've got that little circle there, it's a NAND gate. So you just work out as an and go the opposite. And so you had to find out what these values are here. So if you've got a positive going into A and a positive going into B here, this is OR, so you'll have a C coming out there. You've got 1 going in there, 1 going in there, and if that was an AND, it would be a 1 coming out, but because it's a NAND, you've got a 0 coming out. And you do the same with that there. And this is on page 129 in the red book. Provide 3 significant aspects that support the value of engineering ports in engineering. So you've got to supply the value, the information on the value of engineering reports, and make sure you include collaboration with that. And so that's on page 35 to 43 in the communications workbook. This question here was poorly done, and this is on page 121, the red book. It's almost the same question. Describe these 3 processes of sampling, quantizing, and digitizing on the diagram below to assist your answers. Now, make sure you use a diagram if the question tells you to, because you'll lose marks. So the first thing you've got to do is sample, and the sampling rate has got to be twice the maximum frequency of the analog wave, at least twice. If you work on bandwidth, it's 3 to 5 times the bandwidth between the waves. So there's the samples there, and then you have to quantize these samples. So you draw a line across there and you see the quantity, and it's 9 volts. And then digitizing is changing the numerical value to a binary code, and that's digitizing. Last question. I'm sorry this is taking so long, but I'm nearly finished now. You've got bending stress. You're asked to find the bending stress on the beam, calculate the maximum bending stress. Remember, bending stress is different to bending moment. And there's a trick to this question, because the bending stress formula is My on I, and the Y is the outermost fiber length, and it's got to be the maximum outermost fiber distance from the neutral axis. So have a look at this. It's a piece of angle, this beam, and you can see the neutral axis is 60 millimeters from this side here, and that's not the maximum distance of the outermost fiber from the neutral axis, because the width there is 150. Take 60 away from 150, you get 90. And so that's the outermost fiber length. And that's how they're going to test whether you know that Y here is the outermost fiber length. Now, to find the bending moment, what I've done here, I've found this reaction there, and then you've got a big force there, so you'd assume that that'd be the maximum bending moment, and so you multiply that reaction there. I found that reaction is 12.14, right reaction. Multiply that by 1.5, and that will get you your bending moment. Now, if I were you, I would find the bending moment there if this is pretty close to that there, because that might be a larger bending moment. So all you do is take moments about that there. So it's 20 times 1.5 minus 12.14 multiplied by 3, and just see what the bending moment is there. But this is a significantly larger force than that. So therefore, it's pretty safe to say that the bending moment maximum is there. So you've got 18 kilonewton meters. Make sure you know that the moment is Newton meters. Substitute in this formula and make sure you put the numerical value for kilo there. That's the outermost fiber. And then it's the second moment of area is being given to you as 8.9 times 10 to the 6 millimeters to the fourth. And it's got to be in meters to the fourth. And remember, I told you, you've got to multiply that by 10 to the minus 12. So this, to bring it to millimeters, to bring it to meters to the fourth. And so that'll bring it to 8.9 times 10 to the minus 6. And so we've got 8.9 times 10 to the minus 6. And that works out to be 184 megapascals. And this is well explained on pages 103 to 105 in the Red Book.